Welcome back to the Networking Mastery Curriculum. This is Stage 8, Lesson 58, and today we're tackling something that's been promised for over 2 decades and is finally, genuinely here. IPv6 deployment in the real world. We'll work through dual stack designs, NAT64, and the transition mechanisms that let modern networks actually move forward instead of just talking about it. Here's the roadmap for the next few minutes. We'll start by unpacking why IPv6 took 30 years to gain traction and what finally tipped the scales. Then we'll compare the two deployment models you'll actually encounter in the field, classic dual stack versus IPv6 only with NAT64. From there, we'll walk through the transition mechanisms that hold up in production and which ones quietly don't. And we'll close with where IPv6 stands today in the major cloud providers and across global adoption numbers. So let's start with the timeline, because the story of IPv6 is really a story of delayed urgency. The protocol was picked in 1995 and standardized by 1998, and then basically sat there for over a decade. The wake-up call came in 2011 when IANA handed out its last IPv4 blocks, but real momentum didn't build until mobile carriers like T-Mobile went IPv6 only around 2020, leaning on carrier-grade NAT64. The blocker the whole time was simple pragmatism. NAT made IPv4 good enough. Why renumber your network when you can just hide everything behind 10 dot space and move on? And that pragmatism shapes the 3 deployment models you'll actually encounter in the field. Dual stack runs v4 and v6 side by side, maximum compatibility, but you're operating 2 networks forever, which is exhausting. IPv6 only with NAT64 and DNS64 is the modern target state. It's what T-Mobile and Microsoft's corporate network run on. Clean internally, with translation only at the edge for legacy v4 destinations. And then there's IPv4 only with carrier-grade NAT, which is where legacy ISPs are stuck. No migration cost up front, but port exhaustion, broken geolocation, and massive logging headaches make it a dead end. So let's look at how that NAT64 plus DNS64 combo actually works, because it's genuinely elegant once you see the flow. An IPv6 only client asks DNS, for example, .com. And when no DOA record exists, DNS64 synthesizes one by stuffing the IPv4 address into the well-known prefix 64.f9b96. The client then connects to that synthetic IPv6 address, which routes to the NAT64 gateway, which strips the prefix and forwards a normal IPv4 packet to the real server. The client thinks it's speaking pure IPv6. It has no idea translation is happening. That's the magic. 0 application changes, 0 client awareness. Now, NAT64 isn't the only attempt the industry has made at bridging the 2 protocols. It's just the one that survived. Take a quick tour through the graveyard. 6 Tortorito, Isotap, all dead, all killed by the same villain, which was NAT punching holes in tunnels that assumed end-to-end reachability. What's left standing? Dual stack, where you run both protocols natively, still the gold standard after nearly 30 years. NAT64 and 464 OSLAT for carrier networks, and MAP-T emerging on the ISP side. The lesson here is brutal but simple. Tunnels through NATs always lose. Native deployment wins. Once you've got native IPv6 in place, the next question is how hosts actually get their addresses. And here, IPv6 gives you 2 very different philosophies. SYLAC is stateless. The router advertises a prefix, and the host builds its own address, either from its MAC via EUI64 or randomly for privacy. DHCPv6 is the familiar enterprise model. A server hands out addresses from a pool and keeps a lease database, so you know exactly who has what. In practice, modern deployments combine both. SYLAC for end hosts and DHCPv6 prefix delegation to hand entire subnets down to downstream routers. Now, if you want to see where IPv6 stopped being optional and became simply how things work, look at the hyperscalers. AWS, Azure, and GCP all offer dual-stack VPCs, and AWS even supports IPv6-only subnets with an egress-only internet gateway. which conveniently replaces the NAT gateway you used to pay through the nose for. And that's really the punchline. Clouds pushed IPv6 not out of idealism, but out of arithmetic. RFC's on 1918 gives you about 17 million private addresses, which sounds like a lot until you're running millions of tenants, and public IPv4 now costs roughly $3.65 a month per address at AWS. At that scale, IPv6 isn't a migration project, it's a cost-saving line item. And once the clouds went IPv6, the actual traffic numbers followed. Google's measuring around 45% of all their traffic over IPv6 globally, up from 10% back in 2017, with India and France both pushing 75%, Germany close behind, and the US sitting comfortably above half. Every major service you actually use is dual-stacked. Google, Meta, Microsoft, Netflix, Cloudflare, all three big clouds. But the real driver here isn't desktops or data centers, it's mobile. T-Mobile, Reliance Jio, and Verizon all run their handsets IPv6 only, using NAT64 and 464 XLAT to translate for legacy IPv4 apps. So if you've got a phone, congratulations, you've been on IPv6 only for years and never noticed. So how do you actually pull this off in an enterprise? Here's a realistic 5-phase roadmap that stretches across about 2 years. You start with assessment, inventory, your apps, audit readiness, get a 48 from your ISP, and update your IPAM. Months 3 to 6. You light up IPv6 at the edge, peering, firewall rules, AOA records, load balancers. Then the bigger lift, months 6 through 12, is dual stacking your internal network, routers, switches, servers, DHCPv6 or SLAC for clients. Phase 4 is where you make sure applications and monitoring actually work end-to-end. And only in year 2 do you start shrinking IPv4. New services go v6 only. NAT64 handles the legacy stragglers, and you reclaim that RFC 1918 space. Now that roadmap looks clean on paper, but here's where real projects stumble. The classic mistake is treating IPv6 like a bigger IPv4, trying to subnet smaller than a 64 or bolt on NAT, which immediately breaks ISIL-AC and neighbor discovery. Just as common, hardened v4 firewalls with wide-open v6 because nobody mirrored the rules. Then you've got apps with hard-coded IPv4 literals, engineers confusing link local FE80 addresses with routable globals, and the silent killer, servers with IPv6 enabled but no AA record in DNS, so clients never even try. Mirror your rules, audit your apps, and always verify with DIG. So let's pull the whole story together. IPv6 took 30 years to land because NAT made IPv4 just good enough. But we're now at roughly 45% global adoption, and that curve is only steepening. You've got 3 deployment models to recognize in the wild: dual stack for transition, IPv6 only with NAT64 and DNS64 for modern greenfield builds, and IPv4 with carrier-grade NAT as the legacy holdout. The old tunneling tricks, 6-4, Teredo, ISATAP, are dead. Native dual stack and NAT64 with DNS64-1, and the real engine behind adoption wasn't enterprise IT, it was mobile carriers like T-Mobile and the hyperscalers, AWS, Azure, GCP, all running IPv6 native internally. And here's your cheat sheet, the terms worth keeping at your fingertips. A dual stack, IPv6 only, and SysAdmin are your 3 deployment postures. NAT64 plus DNS64 is the translation pair that makes IPv6 only networks actually usable, with the well-known prefix 64.F9B 96 from RFC 65 464 XLAT adds a client-side CLAT for apps that still hardcode IPv4 literals. And for address assignment, SLAC handles it statelessly via router advertisements, DHCPv6 tracks it server-side, and EUI64, embedding the MAC into the host portion, is effectively deprecated now for privacy reasons. That wraps lesson 58. Next up, we shift from addressing to observability, NetFlow, SNMP, and modern streaming telemetry, all tied together in the final capstone that closes out this 60-lesson journey. We're one lesson away from the finish line, so I'll see you in lesson 59.